Hey, welcome back to Fan Mama Physics. In these two videos, we are going to talk about momentum. Momentum. I want to start off with a question for us. Take a look at these two pictures. We got an elephant here, we got a little bird here. Which one do you think is harder to stop? If you're thinking about the elephant, you might be thinking that, oh, it's a very massive, it's a very large, and it's gonna really hurt if you want to try to stop that. And maybe some of you might think that, hey, it really depends. It depends on how fast this little bird can be moving too. If it's moving, say, at sonic speed or at Mach 3, which is 3 times the speed of sound, then it can also be hard to stop. And you're absolutely correct. Although it might be physically impossible for that bird to go at that speed, but maybe in the vacuum. Let's say in the vacuum. I think air resistance is going to take over. Anyway, sorry, let's talk about this. The fact that you're thinking about two things that could affect whether or not it's harder to stop is, first of all, you have the mass, which in the elephant definitely has that. And you have the bird, which doesn't have a lot of mass. But what if it's traveling at a very high speed? It can also be very hard to stop. And that's the essence of momentum. If an object has a lot of momentum, it can either have a lot of mass or it can either have a lot of speed. Either way, the larger the momentum, the harder it is to stop this object. I'm going to talk more about the harder to stopping and relating that to force later when we talk about impulse and change in momentum. But today we are just going to talk about what is momentum. Momentum is described by an object's mass times its velocity, and that's it. That's it. Is that as simple as that? The key thing about momentum here is that it is a vector, which means not only it has magnitude, it has direction. So whenever you are writing a momentum, recording it, you must include directions. Because I don't know how many times I want to talk about this, because every time I've been marking quizzes, tests, and whatnot, students have missed writing the directions for the momentum and losing marks here and there, and it's very, very painful to watch. So please don't forget directions, okay? So units of momentum, we either use the mass times the meters per seconds, which is just straight from the definition, or you will learn why it is, but we also use newtons times second, and that's something we will talk about later, not today. Another key thing that I want you to pick up for momentum is the fact that it kind of sounds like Newton's first law, doesn't it? An object will tend to stay in constant motion, rest or constant velocity, unless acted on by an external force. If my object has more momentum, it's going to want to stay in constant motion. It's going to be a lot harder to have an external force to change the way it was moving before, or lack of moving if it's at rest. It's if you're thinking of the word inertia, we're onto something, because inertia and momentum kind of share similar properties. And you're absolutely correct. If something has a lot of inertia, it's harder to get it to move. If someone has a lot of momentum, it's harder to stop it or to change its motion. And this is a common theme that we will touch on in this momentum unit. The fact that the topics we talk about momentum are going to sound like Newton's 3 laws. And that's something that I want you to keep in mind of when we are tackling this unit, okay? But we're on momentum today. We are just going to talk about examples, going over examples. I will do example 1. Here, I have an example, 2 examples. I will do example 1. You will get to do example 2. And yeah, I'm sorry, it's a little bit more work, but I promise it won't be too difficult. So let's start with example 1. First, we're going to calculate the momentum of a 6.2 kilogram pumpkin traveling at a velocity of 5 meters per second west. So here are the directions. It even says in the question. So what is momentum? Momentum is your mass times your velocity. And here we have the mass of 6.2 kilograms. Here we have the velocity of 5 meters per second west. Putting that in, and then we put 6.2 times 5 gives us 31. And our units are going to be kilograms times meters per seconds, and going to the west. You can you can also use Newton times Newton times seconds. That's fine as well, okay? Since these examples are already very short, I will just talk through them, but if you're doing example 2, please pause this video right now. And now it's my turn to go over it. Example 2, a baseball of mass 0.14 kilograms is moving at 35 meters per second. Here is the velocity, and we take the mass times the velocity, which is just 0.14 kilograms times 35 meters per second. We get 4.9 kilograms times meters per second, and let's double check the directions. It doesn't say. Okay, so if the question doesn't say the directions, you get a freebie. Okay, you get a freebie. Here I'm just going to put a positive sign in front in case we have the baseball traveling in the opposite direction, which it's not, luckily. B, find the velocity at which the bowling ball, mass, okay, a new object here, 7.6 kilograms, would have the same momentum as the baseball. Okay, so the baseball's momentum is up here. We have 4.9 kilograms times meters per second. Okay, so then we want to find the velocity this time. Here I have the momentum of the bowling ball with a W equals to the mass of the bowling ball times the velocity of the bowling ball, W for bowling. And to solve for the velocity here, we need to divide both sides by the mass. We get the velocity of the bowling ball is equal to its momentum divided by its mass. We can then put our values in here. The top is just 4.9 kilograms times meters per second. The bottom is the mass, 7.6 kilograms. And putting that in our calculator, we get 0.6447. And we're going to round that to 2 sig figs, so 0.64 meters per second. And since no directions are listed, I'm going to write a positive sign. So notice that if I have a more massive object traveling at the same momentum, it's going to be traveling at a very much smaller speed. So that 0.64 meters per second versus 35. That's a big difference. And that all comes down to the mass of this object if they have the same momentum. Okay, so great. These are 2 examples. Hopefully you find them not too difficult. We have one more set of examples coming up in the next video. I thank you for watching and see you next time on Fat Mama Physics.